Climate Change Lecture Series. Welcome to our Climate Change Lecture Series. 2021 is a really important year for this planet. It is a year of climate action. It's the year in which the United Nations Conference of Parties is being held in Glasgow in November. At that conference, decisions will get made that impact the rest of us for the rest of humanity. It is a year since we first began this lecture series with a lecture from Professor Edward Hanna. However, his was the only lecture we delivered at that time before lockdown, and we had to abandon in-person lectures. And so I'm really delighted that we can now restart our climate change lecture series with a lecture from Professor Edward Hanna. He's our Professor of Climate Change, of Climate Science and Meteorology here at the University of Lincoln. He's a Fellow of the Royal Meteorological Society and the World Meteorological Organization representative on the Ice Sheet Mass Balance and Sea Level Expert Group. Really important stuff. He's also an expert on understanding the weather patterns and how these are impacted by climate change. Today, he's going to talk about the climate crisis and critical engagement in Lincoln. As you listen, please do put questions into the comments section. And our plan is to leave plenty of time at the end of Edward's lecture where we'll try and answer as many of your questions as we can. So I hope you all enjoy this lecture. I know it's going to be brilliant. And thank you so much for listening. Over to Edward.
Thank you very much for that introduction, Libby, and thanks everyone for coming along online to this lecture. So I'm going to talk about the climate crisis from a quite general point of view, highlighting some facets of research that I'm involved with, but also other people in my group and in the School of Geography as well, and in particular how we can engage with the wider community to try and address some of these issues. So that's just the synopsis of the abstract of the lecture, which I think you've all been circulated. So obviously it's getting on for about 18, well, almost a couple of years since the university declared a climate emergency, and the City of Lincoln as well. And in line with many other organisations, this continues to be an increasingly important topic, despite obviously other important happenings around COVID and so on. This is an updated version of a slide that I showed you last year, which is showing levels of greenhouse gases in Earth's atmosphere, specifically the concentration of carbon dioxide. As measured at one of the observatories in the middle of the Pacific Ocean. So you can see here Mauna Loa, which is on one of the volcanoes on Hawaii. And direct measurements go back to the late 1950s. And this is in parts per million of atmospheric CO2 concentration. We're now currently about 415, having risen from 315 in the late 1950s. And if you put that in context with the graph on the top right, the present day, you can see with the big blue arrow with the mouse cursor, hopefully you can see that on the top right of the slide, then this is now a time scale going back for 800,000 years, showing levels again of atmospheric carbon dioxide concentrations with natural fluctuations over the last 800,000 years. It's a very small timescale text, but it's this is 800,000 years ago on the left of this graph, and then this is the present day on the right of this graph. And you can see that the very recent levels or increase in carbon dioxide, which is in the last couple of hundred years or so since the Industrial Revolution, is completely unprecedented in terms of natural variations over most of the last 1 million years. So this is a very unusual chemical composition of the atmosphere that we've tipped it towards. And necessarily, when you do that, there's other greenhouse gases as well, but CO2 is the main one affected by human activity. together with methane, you're fundamentally changing the physics of the atmosphere, the amount of heat energy that's trapped in the lower layers of the atmosphere. Now, I was kind of hoping, in line with many other people, that with the recent, obviously the incidental COVID pandemic, that's obviously our travel has been curtailed quite widely across the world, that would have some impact on the greenhouse gas levels in Earth's atmosphere. Indeed, there was a almost 9% reduction in global carbon dioxide emissions from human sources in the first half of last year. So there's a paper published on this in the last few months. In fact, there's several papers. But in terms of translating those that slowdown in global emissions, that's actually only for the first half of last year. I think for the year as a whole, it's only a few percent, 3 or 4%. But because there's a lot of inertia in the system in translating those emissions into growth levels of greenhouse gases in the atmosphere, there's no sign of a slowdown in the growth rate or the accelerating increase in atmospheric levels of CO2. So this graph here is really just amplifying this bottom graph from the previous slide by looking at the last 5 years of, 6 years of global carbon dioxide atmospheric concentrations. And you can see there's no real sign at all of any slowdown within the natural variations over that last 5 or 6 years. So it's had a very minimal effect in terms of the pandemic changes to human behaviour affecting the greenhouse gases in Earth's atmosphere. So that's quite an interesting sort of null result, if you like. And of course, what happens with these increases in greenhouse gases in Earth's atmosphere is they're trapping in more heat near the surface of the Earth. So if you look at these kind of global temperature graphs that are regularly updated, again, this is a very recent update to the graph that I showed you last year, to those of you who came to the lecture then. Global average temperature since the year 1850, in terms of changes, these aren't the actual temperature values, but they're differences or changes in how much the temperature's changed in the last 170 years or so. And you can see an accelerating increase in the last few decades. And notably, the year 2020, last year, was within the sort of margins of error, estimated to be the second warmest year since 1850. So again, this is sort of marking this inexorable upward trend with the global temperatures. A lot of this is responding to human influence through increase in greenhouse gases and all the amplification, the ways that is amplified in the Earth's climate system. And of course, many of you will have seen graphs like this from the maps like this from the Intergovernmental Panel on Climate Change, where the top two maps show two different scenarios of how average surface temperatures are likely to change by the last 2 decades of this century relative to recent levels. So we've got RCP 2.6, which is a low emissions pathway for how human greenhouse gas emissions change going into the future. And then RCP 8.5, which is a high greenhouse gas emissions pathway. So there is quite a considerable range of projections from these computer models of how much average surface temperature is likely to change by towards the end of this century. But some of the higher end estimates suggest quite startling increases in or additional increases, I should say, in global mean temperature, up to between 5 and 7 or 8 or even more in the polar regions degrees Celsius above recent levels by the end of this century. And of course, they're accompanying changes in other parts of the climate system. You can see the lower two charts are showing change in average precipitation by the 2080s and the 2090s relative to recent levels. Many parts of the world get wetter, but the subtropics are predicted to get increasingly drier, as you can see from the brown colours there, enhancing problems with floods and droughts in various parts of the world. And of course, many extreme events have also been amplified in recent years. So this is a very recent, again, update of a graph by the global reinsurance company Munich Re, which is showing various the numbers of natural catastrophes that they define for economic and related social losses. And the total line, the yellow line, is the one to focus on. You can see that you've got something like a tripling of the number of these events in the last 40 years or so. The graph starts in 1980, goes up to last year or so. And actually, a lot of these natural catastrophes are linked with hydrological events, the blue line, meteorological events, the green line, and climatological events, the red line, all of which are trending upwards. And it's only the geophysical events, the earthquakes, volcanoes and tsunamis, which are trundling along on a fairly even keel. But the ones that are influenced by climate, there's partly is human pressure on land use, but part of it is many of these extreme climate events have increased in number and severity over those last few decades, linked with the global warming that I've just been speaking about. Of course, there always have been natural events and disasters, and of course, a very famous one in the Lincolnshire region and more widely in eastern and southeast England and the Netherlands and this part of northwest Europe is the North Sea flood of 1953, winter 1953. When there was a severe storm surge that pounded the English east coast and also the Netherlands, where actually even far greater number of people were killed. You can see the sort of levels of the vertical rise of the tide above the predicted value between 2 and 3 or even more meters, breaching many coastal defences, killing over 300 people in England, flooding 24,000 homes. The coastal defences were less good then than they now are. And then salt contamination of a huge area of prime farmland in Lincolnshire and adjacent regions of eastern England. So, of course, we always have had severe weather events and the impacts of those. And here's another one, Storm Xavier, and Professor Mark Macklin is going to be talking about floods and climate change and related topics in a few weeks' time as part of this lecture series. So I don't want to steal his thunder, but just to briefly mention that these events are ongoing. So this is a more recent occurrence of a Storm Xavier. You can see a similar low pressure system that's drawing the water down the North Sea towards the east coast of England. There's some kind of tidal surge here, flooding 800 homes in Boston. You can see a picture here of the stump church in Boston. And in some parts of the east coast, that was the biggest such storm surge since 1953. These events continue to occur. And of course, Lincolnshire is particularly vulnerable because of the low-lying nature of the land here. And this is just showing the location of Boston. And of course, Lincoln is up here with the yellow dot. But much of this land is effectively very near, within a few meters height, or 10 meters or so of sea level. So you only need relatively modest increases in sea level that I'll talk about a bit later that can occur with global warming to get danger of inundation of much of this kind of coastline. So global sea level currently rising about 3.5 millimeters per year. Here is some data that shows relative changes in global sea level in millimeters over the last 120 years or so, from a combination of tide gauges and more modern satellite altimeter data, where they actually measure the height of the sea surface repeatedly from satellites. And the main causes of this increase in global sea level rise is the global warming that I've mentioned earlier. So there's a natural, what we call a thermal expansion of ocean water that naturally occurs, that's responsible for something like half of the recent or current sea level rise. And a lot of the rest of the sea level rise is down to increasingly melting of the large ice sheets in Greenland and Antarctica, and also of smaller mountain glaciers. So that is an accelerating rate relative to earlier decades in the earlier on in the 20th century. So the sea level rise something like doubled in the last 50 to 100 years in terms of the rate of sea level rise. And you can go on to various websites like Climate Central, and some of these maps featured in various reports in the Guardian newspaper and elsewhere a few years ago, that you can play with the websites for various scenarios moving forward of greenhouse gas emission scenarios, whether you choose low, mid-range or high-level projections. And so on. You can actually, this is actually for a fairly modest, this map here with the red colours showing inundations with sea level rise by the end of this century for a fairly modest rate of continued global warming. So this is under the RCP 4.5 scenario, which is a mid-range intergovernmental panel on climate change projections, something like 2 degrees Celsius warming above pre-industrial. So this is by no means the most severe scenario in terms of sea level rise, inundation threatenings that could potentially occur by the end of the century. Of course, a lot depends on things that Professor Macklin is likely to talk about, things like flood defences and so on that are quite crucial here as well. And speaking of these, this is a picture that photoed I took. We do a lot of field work in the School of Geography and elsewhere in the university on the East Coast with various stakeholders. So this is the seawall at a place called Rangel Bank near Frisney, which is just a few kilometres north of Boston. You can actually see the sea in the background. And this is a flooded area of land that's actually in between two sea walls, which is quite interesting. And then you've got salt marsh on the right-hand side of the picture. And agricultural land, some prime agricultural land, which is about 0 metres above sea level, is on the left, protected by these two sea walls, which is quite a scary thought. But it's amazing the social and economic value of these very near and potentially vulnerable coastal areas, of course. So another factor that I need to mention in relation to how climate change is affecting extreme weather events now and may affect them going into the future during the rest of this century is the jet stream, which you can see as a ribbon of yellow and red. So you can see where my mouse cursor is, which is moving from west to east generally across the North Atlantic Ocean on this slide here. There's a number of factors that can cause the jet stream to vary, but the main causes of the jet stream are the temperature difference between the equator and the poles, which drives the airflow a bit like a heat engine, and also the rotation of the Earth are the basic forces that drive that jet stream. But there's a number of influences that can either push the jet stream further south, so these blue arrows moving down the slide, or push it further north, so the blue arrows pointing upwards on the slide. And so these are just some of the main influences which can affect the jet stream. So I will focus on some of the Arctic influences. So things like the amount of snow cover in Siberia in the autumn season. That if you get more snow cover, that can influence the high pressure over Scandinavia, and through some teleconnections in the atmosphere, feedback on the North Atlantic jet stream and push it further south and weaken it. Similar with the amount of sea ice in the Arctic Ocean, which has been declining very rapidly, as I'll show you in a moment, in the last couple of decades or so, that with a loss of Arctic sea ice, that can also, in effect, weaken the heat engine and weaken the jet stream and push it further south. El Nino in the tropical Pacific Ocean. This can also affect something called the polar vortex, which is a band of strong winds that forms surrounding the North Pole each winter due to the great temperature contrast, particularly high up in the atmosphere between the low latitudes and the high latitudes. And for affecting that polar vortex, it can then weaken the jet stream in the North Atlantic and push it further south. And there's other factors near the bottom of the slide that can strengthen the jet stream and push it further north. So if on the other hand, the polar vortex that I've mentioned strengthens, then this can have the opposite effect on the jet stream through pushing it further north. If you have a warming of sea temperatures in the Atlantic Ocean, this can have a similar consequence. And then tropical volcanic eruptions, these emit clouds of aerosols high up into the atmosphere, several tens of kilometers above the surface, and these can temporarily spin up the polar jet stream and push it further north in the North Atlantic Ocean. So it's a sort of a combination of it's a bit like a tug of war, several different factors competing to influence the jet stream, which in turn controls where you get your high and low pressure systems being formed near the surface of the Earth that you see on weather charts on the internet or on the TV, and in consequence, the extreme weather events that we experience in various places on the Earth's surface. So some work that we've been leading at the University of Lincoln through a former postdoctoral research assistant of mine, Dr. Richard Hall, we've been looking at these factors in some detail, also working with the Met Office and other partners. As I mentioned, global warming, it's not the same everywhere. It's stronger in some areas than others, so greater levels of warming. And if you look at this graph near the bottom of the slide, this is actually from a recent report that I helped produce that's updated each year by the USA National Met Service called NOAA. If you look at these are the changes in temperature in the last 120 years again. The global temperature increase is shown by the blue line, but if you take the region which is north of 60 degrees north latitude, so the Arctic region, according to some definitions, there's no exact definition of the Arctic, but above 60 degrees is one definition, then if you average the temperatures in that area north of that line of parallel, then you get the red line. So these are the Arctic temperature changes, and you can see that in the last since about 1990, the Arctic warming is about double the average global warming for the world as a whole. And there's very good reasons for this, which involve losses of ice and snow, which amplify the warming of the surface and feed back to the atmosphere, accelerating the warming, and other feedbacks or amplification processes that accelerate the warming. What you can do is you can put this kind of graph in map form for the winter season on the left, so December, January, February. This is showing how much warmer the winters were during the years 2007 to 2018 relative to an earlier baseline 30-year average of 1971 to the year 2000. You can see that we've actually very, very strong or warm temperatures anomalies or differences in the parts of the Central Arctic Ocean, particularly in this area around Spitsbergen and Svalbard and going towards the Russian Arctic coastline. And these are areas that have experienced particularly rapid sea ice losses, and therefore effectively you're radiating much more heat from the ocean to the atmosphere. So this is why you've got a hotspot of warming here. So some of these areas in the Arctic during winter are something like 10 degrees Celsius warmer in the last decade or so relative to the late 20th century. That's a huge difference. And then the summer warming, which is shown on the right, is not as great as the winter warming, but you're still talking in many areas of the Arctic, something like 1.5–2 degrees of warming in the last decade relative to the late 20th century. And of course, this is linked with the a much greater probability of extreme events such as heat waves occurring and the impacts of those. So if you look at actually last year, quite an interesting one was what happened in Verkhoyansk in central Siberia, that experienced a new record temperature of 38 degrees Celsius. In terms of old school money, that's 100 degrees Fahrenheit on the old temperature scale, that was recorded as a new temperature record. So quite an unusual, notable new temperature record. And in fact, a high profile paper has just been published on this. but also we had warm conditions for several months on end during the spring and early summer in much of this Russian sector, Siberian sector of the Arctic. And as I say, it's these kind of what we call feedbacks or amplification processes that are responsible for some of this extreme warming in the Arctic. In particular, the loss of the frozen seawater, the sea ice, where in the summer season, so in the month of September, the red line each year is shown by a small red square. This graph goes from 1979 to 2020, so it's against very recent graph. And in fact, last year was the second lowest sea ice on record for that month of September in the satellite record in the Arctic Ocean. But with something like 13% decade loss in the late summer Arctic sea ice coverage. So averaged over the 4 decades of satellite record, that's about half of the area shrunk by about half. But the ice has got thinner as well. So in terms of the volume of sea ice lost in the Arctic Ocean in the summer season, something like 3/4. That's a colossal change. And essentially, several studies are predicting that we're likely to lose essentially all of the Arctic sea ice in summer by within the next 10 to 20 years. And winter, the black line, that's going down very significantly as well. Not as fast as in summer because the winter ice is thicker. It's a bit more resilient to global warming, but there's signs that too is beginning to decline more quickly in the last years as well. And this is just a picture that I took of sea ice north of Alaska a long time ago, it seems, pre-COVID, when we were still going to conferences and things. Perhaps this might change some of the behaviour of scientists, that we do have a responsibility collectively, I think, to try and do meetings more efficiently and perhaps travel less than we used to. So perhaps COVID might change some wider things for the better good as well afterwards. So what happens when this sea ice declines is in the Arctic, it's marking this very strong warming, and accelerates the very strong warming in the Arctic. If you just go back to this picture that I took, then the seawater, which is in between the sea ice floes, this is seawater, much darker under normal sunlight conditions. As you have more seawater, this is absorbing much more heat energy from the sun. And so this is one of the main reasons behind the very strong Arctic warming relative to the average global warming. If you warm the Arctic more than latitudes further south, if you think about it, the tropics are always, at all times, the warmest part of the world. But if you warm the Arctic more than you're warming the tropics, you're reducing that north-south gradient of heat, aren't you? And that north-south gradient of heat is one of the main factors that is driving the jet stream in the atmosphere that I've already mentioned. So as you reduce that sort of weaken that heat engine, then it doesn't happen all the time, but you increase the probability that the jet stream can slow down, become wavier, and meander more for longer periods of time. And in turn, these sort of meanderings can lead to unusual weather conditions further south, such as in mid-latitudes all around the northern hemisphere. So latitudes such as Lincoln, for example, but across Eurasia, across North America, China, Japan. So all around these sort of densely populated, in many regions of the northern hemisphere, where you've got several hundreds millions of people living, that can be directly impacted by some of these changes in the jet stream. So what also can happen is that you have pockets of Arctic air that can push further south than normal into the lower latitudes, and on the other hand, you can have in other places around the course of the jet stream pockets of mild tropical air that can push further north into the Arctic. So it can kind of produce topsy-turvy weather patterns for longer periods of time than perhaps occurred a few decades ago. And some evidence that this is happening in our part of the world, so to speak, is seen in this left-hand diagram here. So if you look at these are both maps of bird-eye views of the North Pole. So the North Pole is in the middle of both of these maps. But if you look at the left-hand map, and the UK is at the top of both of these maps, but if you look at the left-hand map, then the jet stream flow is working anti-clockwise around these maps, and the jet stream is marked by the boundary between the light blue and the dark blue on these maps. So it's around where the cursor on the mouse is going. But around the top of the map, so that's to say over the North Atlantic Ocean and Iceland and Greenland regions, you can see that on the left-hand map, which is representing average summer conditions in the last 14 years, so the years 2007 to last year, you've got a much wavier jet stream configuration than on the right-hand map. If you look at that boundary between the light blue and the dark blue. So the right-hand map is the late 20th century 30-year average, for the average of the summer jet stream conditions for the years 1971 to the year 2000. So there is some evidence from observations that we are seeing some of these conditions. Also looking at shorter term events as well as climate average data, we can also see some evidence of this as well. And in fact, what you'll also notice in this left-hand map is a green blob over Greenland in the recent summers, in the last 14 summers, that didn't occur in the earlier summers. And what is happening basically is a bit like putting a giant boulder in a river, is that we're having, sorry for the reverse, we've got the UK at the bottom now on this map, but we've got Greenland's here, which is, I've drawn this sort of black polygon around Greenland, and we've got a big red blob over Greenland and a blue blob over the UK. But what this red blob is marking is, again, this is for the same range of, similar range of years as on the left-hand map on the previous slide, is a greater amount of high pressure over Greenland in these recent summers. And the right-hand graph, this is showing basically a measure of the intensity or strength of this high pressure over Greenland in the last 170 years. And you can see in the last 2 decades, the last 15 years in particular, we've had record levels of high pressure over Greenland, very unusual compared with all the rest of that time period. And again, that's what's represented by the big red blob over Greenland. So this is for the summer season, June, July and August. So this is directly connected with having this wavier jet stream flow. What happens is that when you have higher pressure over Greenland, you push the jet stream further south over the North Atlantic. You make the NAO more, the North Atlantic oscillation, which is one measure of the jet stream, becomes negative. You're weakening the jet stream, pushing it further south. You can see on this map here, the sort of boundary between the dark blue and the light blue is further south in the recent years relative to the right-hand map. And you're also giving lower pressure, so bluer colours over the UK at the same time that you get this higher pressure over Greenland. So what is happening over the Arctic doesn't stay in the Arctic. It's directly connected with changes in the jet stream further south over the North Atlantic, over Northwest Europe, and impacts on extreme weather that you get downstream, so to speak, of Greenland. And in fact, this increase in higher pressure over Greenland, that, if you like, my group sort of made that discovery through a series of papers in the last few years. That's represented. These 3 lines are from observational data showing the recent increase since the year 1990 in high pressure over Greenland. If you look at what computer models of global climate change are showing in terms of how that high pressure varies, they're not showing an increase. They're showing actually not much change or even a slight decrease. So the increase that we've observed in what we call Greenland blocking, so this is the amount of high pressure over Greenland in summer since the year 1990, is not captured by the global climate models. The whole series of these models is called CMAP. That's just an acronym for all the modelling centres around the world putting together their model results. So in other words, there's a discord or disconnect between what the observations are showing, what my group's work has shown, and what the global climate models are showing. So this is one of our very recent papers that's just come out a few weeks ago on this. So at the global level, the climate models perform very well in terms of predicting global mean temperature changes. But regionally, there are some holes still or some deficiencies. So those can have some quite important effects over the North Atlantic region, for example. And if we look at what was happening 2 summers ago, or the summer before last summer, so in summer 2019, Then thinking back to that summer, there was a strong heat wave, new record temperatures over many parts of Europe during June and July. France got up to about 45 degrees Celsius. Cambridge Botanic Gardens at the end of July, 31st of July 2019, recorded a new all-time UK national maximum temperature, 38.5 degrees Celsius. But some of this warm air that was over Europe, actually, in a very unusual configuration of the jet stream, actually reverse direction over the North Atlantic, flowing over north of the UK and northwest Europe, over Iceland towards Greenland. So this was a very unusual airflow where the jet stream was actually flowing east in a kind of a loop for a few thousand kilometres over the North Atlantic, and actually transported some of this air mass and very high record-breaking heats in relative terms over Greenland towards the end of July and very early August 2019. So we had a record melting episode of the Greenland ice sheet in 2019. Again, this shows how some of these extreme weather events, north and south, can be connected. There was if you like, a direct spin-off of the strong heat wave that we had over large parts of Europe in summer 2019. And a consequence of that, obviously we're well aware of wildfires that have increasingly occurred in various locations around the world in the last decade or so. Some of that is obviously changes in land use management, but some of it's climate related. So if you look at what's been happening over Greenland, where there's relatively minimal human impact on the environment, there's only about 50,000 people living in the whole of Greenland. That's the size of several of the larger European countries. Then we had two extreme fire years or episodes in 2019, which was when we had that record heat in Greenland, and also a couple of years before in 2017. So this is a NASA image of some of these plumes from the fires in Greenland. And a consequence of getting these changes in high pressure over Greenland in summer and in winter, I'll mention winter in a moment, is that you can change, as I mentioned, the jet stream over the North Atlantic, which in turn can change the chance of getting extreme weather further south in parts of Eurasia, for example. So this is just looking at some of the impacts in summer and winter over the UK. So in summer, if you look at the lower right plot here, this is showing the effects on the amount of summer rainfall of having more high pressure over Greenland. You increase on average, not all the time, but on average, the amount of summer precipitation over England and Wales. Not so much Scotland, because the jet stream is pushed further south. And in winter, with more high pressure over Greenland, actually we've got extreme high pressure over Greenland as I'm speaking, then you tend to get these easterly cold air outbreaks. So you can see some cold or low temperature anomalies on the top left plot here. So again, this is illustrating that these events or weather events in different latitudes are connected. And if you get a trend in what's happening over the Arctic, this can have unexpected consequences with what's happening at lower latitudes and downstream over parts of northwest Europe, for example. And in fact, June 2019, we had the Wainfleet floods in Lincolnshire, quite near Lincoln. You can see locations marked with the red arrow here. These are the percent of average normal June rainfall that were experienced in June 2019. It's almost or about double the long-term June average in large parts of central England, Wales, parts of further south in England as well. What was interesting about this June was that we had a near record high pressure. The weather chart on the top right of the slide shows the second strongest high pressure region that was experienced in this particular climate record that goes back to 1948 for the month of June in that 70-year record. And also in the subsequent year, we had many other record-breaking rainfall events that were also connected to, obviously directly connected to what the jet stream was doing, and in turn what the high pressure over Greenland. So, for example, autumn 2019, we had floods in the Brayford Pool. Luckily, narrowly avoided flooding the university, thank goodness, but north of the Brayford was partly flooded, and obviously much more severe floods quite near Lincoln as well. But if we look at what the autumn was doing, that had the third highest measure of autumn high pressure in that climate record. So this is the flooding on the north of the Brayford. So what we've seen now, winters have got more extreme in the last couple of decades or so. This is one measure of the jet stream, how it fluctuates between years over the North Atlantic Ocean. We've seen increasing fluctuations from one year to the next that are statistically highly significant, something like a doubling of the year-to-year variability over the last century. So you've got more extreme oscillations between cold, dry winter episodes, so the one that we're experiencing at the moment, also with some snow, and mild, wet, stormy episodes with record-breaking floods at times. So this is a more severe episode of the current episode, this the so-called Beast from the East, severe snowy episode that particularly affected Lincolnshire, other parts of the country in February and March 2018. On the other hand, we've had record-breaking, severe, mild, stormy, wet winter episodes as well in the last 10 years. So last February, for example, February 2020, was the wettest February on record in the UK, linked with a very strong jet stream and the second highest North Atlantic oscillation, which is a measure of the how uniform or strong the jet stream is in the climate record going back to 1948. So more extreme winters. This is from some of our research. The final thing I want to talk about in the last 3 or 4 minutes is some work that my group's been doing, looking at changes in the ice sheets, particularly the Greenland ice sheets, and how they can contribute to rising sea levels. So this is a schematic of an ice sheet showing mass gain through snowfall each year that helps the ice sheet grow, but then there's also mass lost each year through melting and runoff of that meltwater and icebergs breaking off around the edges of the ice sheet. So it's a bit like a bank balance, really, in terms of working out the mass balance or mass budget of an ice sheet. So there's only 3 ice sheets in the world, 1 in Greenland, 2 in Antarctica. There's lots of smaller glaciers, but I'm really talking about the Greenland ice sheet now, which is what most of my group's work has focused on. So we run various computer models of the mass balance, the surface mass balance, looking at the amount of snow or precipitation falling on the ice sheet each year, minus the amount of melting of the ice sheet each year, to try and help these sort of mass balance estimates. So looking at this, the meltwater, the runoff in yellow here, just put the mouse cursor on again, this has doubled in the last 4 decades. So this meltwater running off of the ice sheets, Greenland ice sheet, has doubled. The scale is in cubic kilometers per year of volume. The surface mass balance has gone down. So the surface mass balance is the precipitation, the snow precipitation minus the runoff each year. So in a direct effect of the runoff increasing is the surface mass balance has gone down. And then if you look at the relation between the surface mass balance changes of the ice sheet and the average summer temperature over Greenland, then there's various estimates that you can produce of that, which feed into predictions, computer model predictions of how the ice sheet is likely to lose mass during the rest of this century and contribute to global sea level rise. So I haven't got time to go into the details of this, but we've recently published some of these results. If anyone is interested in reading into it, then there could be 10 to 20 centimeters of global sea level rise from increased loss of mass from the Greenland ice sheet during the rest of this century. And in fact, if you look at the Antarctic ice sheet, the top graph, these coloured lines are all different estimates from different satellites and so on, of in billions of tons per year of the Antarctic ice mass loss in the last 30 years. The bottom graph is showing the same for Greenland. If you take all 3 ice sheets together, remember there's 2 ice sheets in Antarctica, 1 in Greenland, then it's something like 400 billion tons of ice has been lost per year on average over the last 10 or 15 years. So that's raising global sea levels by about 1 millimetre per year, which is about a third of the total current global sea level rise. And some indications from the Intergovernmental Panel on Climate Change from a report they published a couple of years ago, that sea level rise may be greater than they predicted in 2013 in their last main report. So potentially up to over a metre by the end of this century under a high emissions greenhouse gas scenario. And there's some things we don't really know very well about the Antarctic ice sheet, but we could be talking about potentially even larger contributions to global sea level rise. But everything's up for grabs, because if we can reduce enough our contributions of greenhouse gases and mitigate some of these emissions, then we could be nearer the lower end of some of these projections. So not all is not lost. I don't mean to paint that picture, but there is a very significant risk that we could get up towards those sort of metre or even potentially a bit more global sea level rise by the end of this century. So, and the last slide I want to show is about the Lincoln Climate Commission. Actually there's many actions that are going on in Lincoln and well beyond, that the university is involved in some of those, and colleagues are going to be talking about these in later lectures. But one activity which was sort of co-founded by my colleague in the geography school, Dr. Andrew Kifriotis, other people in the university involved, together with the City of Lincoln Council and businesses across the Lincoln area, is to set up the Lincoln Climate Commission. And this, through meetings, influenced the City of Lincoln Council to achieve to target a net zero carbon by the year 2030, which is a very ambitious target, but which is significantly influenced in the City of Lincoln Council's ambition directly influenced by research in the university. So with that, I'm out of time. I'm going to end it there and open it back up to Libby and for any questions. Thank you very much.
Thank you. Absolutely tremendous. So a real tour de force of some of the things we now understand about our climate and the interaction between climate and weather and how that will impact on us. We do have some questions, which I'll come to in a second. So we've had a question about whether the slides can be shared.
Absolutely.
Actually, they can be, but you'll have to write to us and let us know your email address. But of course, all of these talks are going to be retained for viewing on demand. So everything that you've seen just now will be available to you. Okay, so we've got a question about the ice core data, Edward, from Luc Bidot, who wants to know, are historical ice core data corrected, or do they need to be in any way to relate to current ones? I guess that was when you showed us right at the outset the carbon dioxide levels and how we've measured it going back into using ice core data.
Yes, that's a very good question. I guess it might potentially be useful to be able to refer back to one of the slides. But yes, I know the slide. Thank you. So yes, so that's a good question, Luke. So the first thing is I'm not a paleoclimatologist, so I'm not an ice core expert. I do work with people at the British Antarctic Survey and in the USA and so on, who directly deal with the with the ice cores, and I've also used some of the data from some of the ice cores, not these very long records on the slide, but some of what they call shallow ice cores dug out from the Greenland ice sheet that represent the last few decades or the last century of snowfall records to test results from computer models that I run of the mass balance of the Greenland ice sheet. So the ice core data are very useful for a variety of purposes, partly reconstructing past environments before we had instrumental climate records, and secondly for helping to constrain computer models. So I do work with those people, but I think you'll have to speak with them to get an honest, or I should say best informed answer there, Luke. But of course, all these sources of data are kind of cross-calibrated against each other.
Okay, thank you. And Luke's asked us another question. By the way, there's lots of congratulations and thanks on the comments, Edward, which is lovely. But I've got another question for you here from Luke, which is, considering the feedback loops and the pace of atmospheric changes, is there any viable way back i.e. not yet involving space-borne solar umbrellas? And if so, what kind of time frame are we talking about? So that's a very interesting and challenging question too. Is this inevitable?
Yes, it is. So as I showed, I mean, the models aren't perfect, but they seem to do a surprisingly good job at the global level. There is a very wide range of predictions of things like just looking at the global average temperature, something as simple but as profound as that on the top two maps here, and how these two maps, which one of these we end up being closest to by the 2080s and the 2090s, depends to a large extent on our behaviour as a species moving forward, and how rapidly we adopt renewable energies, even more going into the future, at the same time as allowing particularly countries that obviously have developed later to develop in a way that we can get their living standards quite rightfully up to speed as fast as possible. So there's obviously a whole balance of factors in play. I think that there is a good deal of hope based on what I've seen from what's happening with the renewable energy industry. I was actually pretty pessimistic 5 to 10 years ago that we would be able to do anything meaningful, that we would have to adapt to climate change, and there is a lot of change already locked into the system. There's no mistaking that. So there will be inevitably degree of further warming, changes in extremes, sea level rise, all of that. But I think we can blunten that a lot through how we, particularly in the next 10 and 20 years, roll out some of these mitigation measures in a way that are economically, socially, politically, and so on sustainable. So it's bringing all these things together to address the climate emergency, and I think we've got the ability, the technological ability to solve all these problems. It's a more political and social question rather than a technological or even an economic question, I think, to a large extent. That's just my opinion, though. So I think there is some hope, but it is it's not going to be easy, even so. But I think what's amazing is what's come out in the last couple of years with things like the university, the City of Lincoln Council, but many other organisations around the world actually getting really serious about responding to pressure from society, from young people in particular, from the school strikes and so on, in terms of declaring a climate emergency. I think there is a kind of there are ways that we can combat this problem. And I think the signs are more hopeful than they were a few years ago, but there's a lot to do, is the short answer.
And it just depends on global leadership too, doesn't it, Edward? Just looking back at the comments, I was struck by your maps of Lincolnshire and how much of it could flood quite soon. And there's a comment there from someone, Graham Hempsall, who facilitated an exercise with Lincolnshire Police, Fire and Coast Guards testing our response to a tidal surge scenario just this morning. So, there is no doubt that flooding will come to Lincolnshire. Yes, this is quite a scary map, isn't it? Especially as those regions in red are really important vegetable growing regions for the UK. There's also a comment from Chris. Very interesting comment. If we stopped all carbon emissions today, and I suppose what you mean, Chris, is that if we evened them out, we take out as much as we put in, so we got to net zero, presumably that's what you're thinking, how long would it take to see a drop in levels in the atmosphere? I imagine we'd see similar levels for some time. So, yes. Edward?
That's a very good question. I'm not an atmospheric chemist, but CO2, carbon dioxide, has a residence lifetime of up to around, I think it's about 100 years in the atmosphere, or 90 years or so, or the half-life or whatever. So you're talking about a lot of inertia in the system. And I think that's one of the reasons why, despite the cuts in CO2 emissions of 9% between January and June last year, that didn't translate to a discernible drop in the actual concentration of CO2 in Earth's atmosphere. So of course it would ultimately make a huge difference in several decades time. So it's important, we can't obviously just stop all emissions immediately, but in terms of what we do over the next decade or two, the flip of that, the reverse side of that answer, if you like, is that it's going to make a massive difference further down line. Whereas if we don't make any changes within the next decade or two, it makes it much harder to cut into changes that are already locked into the system.
Yeah, thanks. Good question and interesting answer. Andrew Kithriotis has asked what our views are on the COP26 that I mentioned at the start, the Conference of the Parties. I think particularly now that America are back in the picture and showing some international leadership in this space.
Yes, I mean, I think obviously Andrew is much more of an expert on that than that's Andrew's field, and some people listening will know much more about the climate policy and politics as well. But I mean, yes, the signs are more encouraging than perhaps they were from that perspective. But it's how we join everything up internationally. So it's obviously far more than just one particular country alone. Although obviously the USA is quite an important player here.
Yes, I agree. As I said at the outset, it's absolutely critical that we do make progress. Interesting question from Matthew Booth, who earlier told us he was listening from Switzerland, which is, what is the single biggest thing that we can do as individuals to support net zero? And I'm going to make this the last question, Edward. So
I think it depends on the individual to some degree and your existing lifestyle. So the biggest change that I can make is to carry on, stop traveling around the world to conferences on field work. I mean, us as climate scientists and researchers, we would argue that some of those trips are fairly important, but there's certainly ways that we could collectively cut back on some of them. And I think we've seen some of the technology and willingness to embrace these kind of talks and the conference format as well that might help meet that. I think it really, there's whole toolkits obviously on how we can individually and collectively embed low carbon lifestyles. So there's books by Chris Goodall and others, for example. I mean, obviously it really depends, because some people, for example, have to use their cars for certain purposes, but then it so much depends on the journeys you make, what vehicle you've got, if you're driving, whether you can use public transport where you live. And obviously things like domestic heating is a really big one, and many of us live in relatively old drafty buildings in certainly in the British Isles, that there are things that you can do, relatively quick gains, loft insulation and secondary glazing, if not full double glazing. Yeah, there's a whole raft of measures. I mean, whole books and websites, of course, that I'd encourage people to have a look at if they're interested. I think even if we collectively do lots of little things, then it's certainly pulling in the right direction, and there's a certain force that then begins to pull other people and organisations along, and also at the organisational level as well. This is quite crucial here. As soon as particular organisations move in a certain direction, and other organisations follow to retain market share and all this sort of thing. So there can be implicit economic pressures and business pressures here as well that can be helpful in what we may collectively set out to achieve with some of our carbon targets. But yes, we can all do something, because none of us is perfect, and it's a process of continual reflection and improvement, I think.
I agree. I think if we all make little steps, we'll get there eventually. And of course, we have to support our government to make those big changes on our behalf as well. And Jeff Stratford has suggested supporting the Climate and Ecological Emergency Bill. Now, I'm going to tell you that our next talk in this series is by Rebecca Forster, who works at the university in our sustainability management team. And that will be all about how you can calculate and manage your own carbon footprint. So absolutely relevant to the questions that were just asked and some of the answers that have been given. And I do hope we'll see you for that talk, which will be next week. And please refer to our talk website for the details of that talk, and I hope we can see you there as well. Oh, she's just popped it up. It's at 11 a.m. Next on the 17th. Carbon conscious, calculating and being aware of your own environmental impact. So perfect for some of those questions. You'll be able to see, if you look at the website, the whole series of talks that we've got planned. But I just want to finish by thanking Edward again. I think that was fabulous. I'm sorry we couldn't get to all of your questions. It just goes to show how much interest there is in this. Please email us if you want to know more or find out more about our work that we're doing here. We'll do our best to get back to you. And Jeff, you're absolutely welcome. It's a delight to present these talks, and I'm really pleased we can do so. We're out of time, so I'm going to say goodbye, and thank you all very much for listening and watching today, and please join us again next week. Bye-bye.